So let's talk about the overhead for pipelining. Say we start out with a processor that takes 100 nanoseconds and 100 picojoules of energy for each instruction. So you've got time and energy. Now, say this is a great processor and it can be infinitely pipelined, but that each pipeline register is going to take an extra 2 nanoseconds and an extra 2 picojoules of energy. So go through and figure out what would the throughput, that is how long it takes on average for each instruction, the latency, that's the total time for each instruction, and the energy per instruction be if we pipeline this to 100 stages and compare it to the original processor, and then conclude, is this a good design or not? Well, let's take a look. Compared to the original processor, well, we've got the numbers here. It's 100 nanoseconds per instruction. It does one instruction every 100 nanoseconds because there's nothing in parallel, it's just one instruction at a time, and it takes 100 picojoules for each instruction to finish. What about the pipelined one? Well, if we pipeline this 100 times, we're going to divide each instruction up into 100 chunks, so it's just going to take 101 nanosecond times to do it. So the latency, if I divide it up, is it's still going to take 100 nanoseconds for each instruction, but now I've got 100 pipeline stages. So each pipeline stage takes an extra 2 nanoseconds. So now each instruction is going to take 300 nanoseconds total to finish. So that's a lot longer. Each instruction is going to take 3 times longer. And why is that? Well, we've got 100 pipeline registers in there plus our original logic. So that really adds up. How about the throughput? Well, we're going to get one instruction out in every pipeline stage, every clock cycle. And we've taken our 100 nanosecond processor, divided by 100, that's our pipelining. So that's going to be 1 nanosecond of logic for each stage, plus we have 2 nanoseconds for the pipeline register. So that means that you're going to have 3 nanoseconds for each stage. And if we keep our processor full, we're going to get one out every cycle. So now if we keep the pipeline full, we're going to get one instruction every 3 nanoseconds. So that's 33 times faster. That's enormously faster. How about energy? Well, energy, we're going to spend still the same 100 picojoules that it took before to do the instruction logic, but now we have 100 pipeline registers too. That's an extra 100 times 2 picojoules per register. So that's 300 picojoules per instruction now. So we've increased our throughput by 33, and we've increased our energy by 3x, and the question is this a good design? Is 33 times the energy, or 33 times the throughput for 3 times the energy a good choice? And to answer that question, go back and look at what we saw at the beginning of class. So we saw this graph here, and this was showing how things changed over time. And the question is 33 times better performance for 3 times energy a good design? And if you look at this here, we can't even do 3 times energy if we wanted to. So this is a terrible design. We can't get 3 times energy, we can't afford it. So even if 33 times better throughput sounds great, we can't afford the energy to get there. So here's some extra problems. So the first one is, what is the speed up for a processor? We have 200 nanosecond clock frequency, and we pipeline it 25 stages with latches that take 2 nanoseconds each. And the second one is, what do you need to get the best performance from a pipeline processor? Well, the answer to the first question here is 20. If we didn't have any overhead from the latches, it would have been 25, because we pipeline at 25 stages. But because we have that overhead, it means each pipeline stage is going to take an extra 2 nanoseconds. So we're only going to run 20 times faster. For getting best performance from a pipeline processor, we need all of these. So if we execute a higher clock speed, that doesn't help because we chop up the instructions, but we need to do that to start with. We need to do multiple instructions in parallel. That's how chopping them up and going faster gets us more work. And if we don't keep the pipeline full, then we're throwing out the performance. So we need to do all of these things to get the best performance from a pipeline processor.